So now we're going to look at another trend as you go across a period and down a group, and this is called ionization energy. This is a trend that we'll be looking at. This is a particular property that we will be examining. And let's define what we mean by ionization energy first. This is the energy required to remove an electron from a ground state gaseous atom, right? So we're talking about the energy that is needed to completely remove an electron from an atom in the gaseous state and also in the ground state, all right? So it's usually expressed in kilojoules per mole of atoms. And just to give you a hypothetical example, so what we're talking about here is the energy required to start off with a gas, M, right? M in the gaseous state, and then you remove an electron to form the cation in the gaseous state. And that is called the first ionization energy. Delta H for that would be equal to I1, which is the first ionization energy. And of course, if there are any other electrons left, we can remove those as well. So if we start off with the cation that we ended up in the first step here, and we remove another electron, then the energy required for that would be the second ionization energy. And then you can have the third, fourth, fifth, if you have enough electrons to remove, all right? And first thing I want to mention here in terms of trends within the same atom with respect to the ionization energy for successive removal of electrons is that the energy required to remove the first electron will be less compared to the energy required to remove the second electron, which in turn will be less compared to the energy required to remove the third electron. In other words, with each successive removal of electron, it becomes more difficult, right? So as stated here, removing an electron from a positive ion is more difficult than removing it from a neutral atom, which makes sense if you think about it. Because if you're removing an electron from a neutral atom, basically that will require some energy. But if you're removing an electron from something which is already positive, then more energy would be required, all right? So that is what is observed right across the board for every atom. Now, what you'll find also when you're looking at the removal of electrons is that there's a large increase in the ionization energy after the valence electrons are completely removed. And here the question is asked, why? Well, the answer is that after removing the valence electrons, then what you have left in the atom are the core electrons, which are closer to the nucleus. And therefore, those electrons would be more difficult to remove compared to the valence electrons. So therefore, significantly more energy will be required to remove those core electrons compared to the energy required to remove the valence electrons, all right? Okay, so let's look at trends as far as the different elements in the periodic table, going from left to right and top to bottom of a group. Now, what we'll be focused on here is the first ionization energy, right? So the first thing we're going to mention here is that as you go down a group from top to bottom, then what you'll find is that the ionization energy, the first ionization energy will decrease. And the reason for that is that as you go down the group, the distance between the valence electron and the nucleus will increase. And therefore, the nucleus will have a weaker hold on the electron as you go down the group. So therefore, it becomes easier to remove the valence electrons, all right? Now, going across a period from left to right, what you'll find is that with exceptions, and we're going to get into those exceptions, but generally speaking, the ionization energy increases going from left to right of pretty much any period with a few exceptions. Why is that so? Well, because as you go from left to right, you're increasing the nuclear charge, and therefore the effective nuclear charge experienced by the valence electron would increase, right? And therefore, it becomes more difficult to remove the valence electrons, and therefore, as a result, the ionization energy increase. The first ionization energy increases as you go from left to right of any period. But there are some exceptions which we're going to deal with shortly. But before we get to those exceptions, let's just look at some data here just to summarize what we just said. So remember we said that after the valence electrons are lost, the energy required to remove the other electrons will be significantly higher. And one can see that, for example, when you compare the ionization energy going from, well, let's look at lithium firstly compared to beryllium, right? So what we have here are the first and second ionization energy for lithium and beryllium. And you'll notice that in the case of lithium, the amount of energy needed to remove the first electron is 520 kilojoules per mole. And then to remove the second electron, it's 7,298 kilojoules per mole. So that's a significant difference. In fact, let me just use my calculator here to give you an idea of how significant a jump that is. So 14 times, right? So basically, the amount of energy needed to remove the second electron is 14 times that of the energy needed to remove the first electron in the case of lithium. Now, in the case of beryllium, comparing the same two, you'll see that, and one can just see it here without even doing any significant calculation. The ionization energy needed to remove the first electron is equal to 900, while in the case of removing the second electron, it's equal to 1757. So that's less than twice the amount of energy needed to remove the second electron compared to the first electron. So why is that difference so small in the case of beryllium compared to in the case of lithium? Well, in the case of beryllium, beryllium has two valence electrons. So the first two electrons that would be removed are the valence electrons. So therefore, 900 kilojoules per mole is needed to remove the first electron, and then 1757 would be the amount of energy needed to remove the second electron. So therefore, those two electrons are being removed from the valence shell. In the case of lithium, however, the first electron is the only one in the valence shell, and that is removed first. That's the amount of energy needed. And then now to remove the second electron, you have to go to the inner core electrons, which are closer to the nucleus. So therefore, that's the reason why there's a 14 times increase in terms of the number or the amount of energy needed to remove the second electron compared to the first in the case of lithium, right? And you can see a similar trend for other comparisons between sodium and magnesium, between potassium and calcium, and so on and so forth, all right? So basically, that's explaining why in the case of removing the valence electrons, it's easier to remove those compared to removing the inner core electrons, all right? Okay, now what we're going to look at here in this table is the trend in terms of ionization energy increasing as you go from left to right, with a couple of exceptions. So we're going to focus on period 2, which starts with lithium and end with neon, right? So what we see here, and we're going to focus on the first ionization energy, which would be the top row of data right here, right? So as you can see, lithium, the first ionization energy is 520, and then it increases to 900, right? In the case of beryllium. And then you'll notice that there's a slight drop off from beryllium to boron from 900 to 801 kilojoules per mole. So this begs the question, why is it that even though boron has a higher nuclear charge compared to beryllium, the first ionization energy of boron is slightly less than the first ionization energy of beryllium? Now, the answer lies in the electronic configuration, which I've written here for both beryllium and boron. And you'll notice that in the case of beryllium, the first ionization energy would require the removal of a 2s electron here, right? Because those are the electrons in the second shell, which is a valence shell, all right? So that's it. So the amount of energy required to remove one electron here from the valence shell would be 900 kilojoules per mole. Now, in the case of boron, you'll notice that in the valence shell, you have 2 electrons in the s orbital and 1 electron in the p orbital. Now, if you remember when we talked about the orbitals and their energy levels, you'll remember that the p sublevel would be of a slightly higher energy compared to the s sublevel. So therefore, the electron that would be lost when boron loses a valence electron would be the electron in the slightly higher energy level of, or sublevel of 2p, right? So therefore, it is easier to remove that electron compared to removing an electron from the 2s orbital, which is on average closer to the nucleus. So that's the reason why the first ionization energy of boron is slightly higher compared to the first ionization energy of beryllium. And that's because the electron to be removed in the case of boron is in a p orbital, which on average would be further away from the nucleus compared to the electron here in the 2s sublevel in the case of beryllium, which would be on average closer to the nucleus, all right? Okay, so if we continue looking at the numbers here going left to right, you'll see that the first ionization energy of carbon is higher than that of boron, so that increases, no surprise there. And then the same thing as we go from carbon to nitrogen, there's an increase in the first ionization energy, all right? No surprise there either. And then we get to nitrogen, going from nitrogen to oxygen. And again, there is a slight drop in the first ionization energy from 1402 in the case of nitrogen to 1314 in the case of oxygen. Why is that so? Well, again, it goes to the electronic configuration, which I've redrawn right here, right? So, or I've written down here, I should say. Nitrogen has this electronic configuration here, and oxygen is 1s2, 2s2, 2p4, right? So, in fact, this is what I'm going to do, because I think I'm going to need a space here. So let me, I want to keep this here because this is in reference to a question that we're going to look at later on. But what I'm going to do down here, way down here, is write down the electronic configuration of nitrogen and oxygen. So nitrogen is 1s2, 2s2, 2p3. And oxygen is 1s2, 2s2, 2p4. All right? Now, what I'm going to do is use the orbital diagram just to represent the 2p sublevel in each of these cases. So in the case of nitrogen, this would be the distribution of the electrons in the 2p sublevel. All right? And in the case of oxygen, so this is for 2p, and in the case of oxygen, this is also 2p. The electron distribution would be 1, 2, 3, and then 4. All right? So when nitrogen is losing an electron, it's going to lose any one of these 3 electrons here, right? And the ionization energy for that, going back to the PowerPoint slide here, the ionization energy for that would be 1402 kilojoules per mole. However, when we get to oxygen, the electron that would be lost, preferentially, would be this electron right here. And you might be wondering the reason why. And the reason why is because this electron is occupying the same orbital as the other electron here in the same 2p sublevel. And what that means is that there'll be some repulsive forces. Because remember, electrons are negatively charged and like charges do not like each other. So repulsive forces will exist between the 2 electrons, right? And therefore, it makes it easier for the removal of the electron that is sharing an orbital, sharing a p orbital. All right? So because you have these 2 electrons here in the same orbital, it is easier to remove one of these than removing any of the others because there's some repulsive force that exists between those 2 electrons. And therefore, the energy required to remove any one of those 2 electrons would be significantly, well, slightly less, actually. Not significantly, but slightly less. So going back to the PowerPoint here, you'll see that there's a fall off in the energy as you go from nitrogen to oxygen. The first ionization energy decreases from 1402 to 1314. All right? Okay, so that's the explanation right here I just mentioned. The repulsion between the paired electrons makes it easier to remove that electron from that p sublevel. All right? Okay, so with that said, let me move on now to the next slide. So what you'll notice here is that that trend tends to be repeated as you go down the groups that I just mentioned, right? Going from beryllium to boron, which is going from group 2 to 3, and then from nitrogen to oxygen, which is going from group 5 to 6, all right? So let me just show you this graph right here. It's a plot of first ionization energy versus the atomic number. So lithium starts here, and as we said before, as you go from lithium to beryllium, the ionization energy increases, and then it drops slightly when you get to boron. And then after boron, you have carbon. you have nitrogen. So nitrogen would be here, right? Hold on, let me see. You have beryllium, boron, carbon, right? Then nitrogen, and then it falls off to oxygen right here, and then it increases as you move from oxygen to fluorine and then neon. So you see that there's a drop here and a drop here, and we explained that already. There's a similar drop for the corresponding groups when you get to the third period, right? So basically going from magnesium to aluminum, and then from phosphorus to sulfur, you see a similar drop in terms of the first ionization energy. But that change becomes smaller and smaller as you go down those corresponding groups, all right? So those are the exceptions to the general trend in terms of what happens as you go across a period. The ionization energy generally increases as you go from left to right of any period. Okay, so let's look at these examples in reference to what we just covered. So again, we are given some elements, and you're asked in this case to arrange each of them in terms of their increasing first ionization energy. Okay, so let's start off with this. So again, we need to refer to the periodic table. So let me bring the periodic table up here. So this is the table right here, all right? So the first series here is magnesium, sulfur, and silicon. So if we look at the periodic table, magnesium is here, silicon is here, sulfur is here. They're all in the same period, right? So remember we said now the first ionization energy increases as you go from left to right. So I would say that the first element, in fact, let me go to my writing pad here. I think I have the, right, same question here. So let me go back here. So the first element, which would have the lowest first ionization energy, would be magnesium, followed by silicon, and then followed by sulfur. So basically, it's for A, it's magnesium, followed by silicon, followed by sulfur, all right? In the case of B, let's again look at the periodic table and look at these three elements. The three elements are arsenic, nitrogen, and phosphorus. Okay, so let's see. Arsenic is here, nitrogen is at the top, phosphorus is in between them. And as we said before, the first ionization energy decreases as you go down the group. So arsenic would be the lowest in terms of the first ionization energy, followed by phosphorus, followed by nitrogen. So it's, in the case of B, arsenic, followed by phosphorus, followed by nitrogen, all right? And then we get to C. In the case of C, it's arsenic, germanium, and phosphorus. Those are the three elements. Let's look at where they're located. Okay, arsenic is here, phosphorus is here, and germanium is to the left of arsenic, all right? So I would say that in this case, the one with the lowest ionization energy would be germanium, because germanium is to the left of arsenic, and arsenic, since it's below phosphorus, would be the one with would have a lower ionization energy, first ionization energy compared to phosphorus. So the answer here would be germanium, followed by arsenic, followed by phosphorus in terms of lowest to highest. So germanium would be the first, followed by arsenic, followed by phosphorus. All right? So that's basically how we would answer those questions. All right? Okay, so